4.5, rational functions and inequalities. Rational functions are huge, and we don't get to them until this point because we have to be really clear about what it is to be polynomial functions. So once we have a clear understanding of polynomial functions, rational functions are going to be fractions that have a polynomial in the top, p of x, and a polynomial in the denominator, q of x. And when we divide those polynomials, knowing that the bottom one, q of x, cannot equal 0, interesting things happen, especially as we approach the values that would make q of x equal to 0. So here's the thing. Because polynomials, not in fractions, but polynomials in general, have domain that goes from negative infinity to infinity, there's probably going to be some value that makes q of x equal to 0. So we're looking at calling f of x our function, but we're going to have a polynomial on the top and a polynomial on the bottom, and there will probably be some x value that would make q of x equal to 0. So maybe it's got 3 factors, and those 3 factors are going to make q of x equal to 0. We would solve q of x equal to 0 and then exclude those. That's why it says implied domain. We exclude those values from the domain, but those turn into important features of our graph. So those values, these sum x values that would make the denominator equal, they become important features of our graph. And we're going to talk about that in this section. But 2 things that I want you to be really clear about before we start this section is kind of a just a general math idea, but I want the idea to stick with you. So let's say that we have any fraction, and we're going to call 2 important ideas about them. We're going to talk about them here, and hopefully they'll make sense as we do some numbers. So let's say, for example, that we have a large number over a small number. And so I'm talking about, say we have, let's start with 5 over 1. Okay, we know that's a whole number. What if we say that we have 5 over a smaller number, like 0.01 or 0.1? What does this turn into? So 5 divided by 0.1, that's going to be 500. That's a much larger number because the small number got even smaller. What if our small number got even smaller? So we're sort of going smaller and smaller in our denominator here. So it's 0.00001. So that's too small for you to do in your head. And so we pull out our trusty calculator and we divide 5 by 0.0001. And we get 50,000. If we divide 5 by an even smaller number, so we just throw in as many zeros as we want, then we get 5e to the 10. So what am I saying here? I'm saying here that as the bottom number gets really, really small, so if we have a large number, and 5 is not even that large, but it's way bigger than 0.0001, over an infinitely small number, meaning we're trying to be 0. We're trying to get really, really close to 0. If we have it infinitely small, really close to 0, then together the fraction is infinitely large. So infinitely, probably should have just drawn the little infinity symbol, infinitely large. So this went up to 5e to the 10. So large over infinitely small goes to infinitely large. As opposed to if we have a small number over a really large number. So if we divide 5, we'll just keep that, but instead we divide by a really large number. So we divide by, let's divide by 100, okay? So that's going to be 1 over 20. What if we said 5 over 1 million? 1 million. Let's see what our trusty calculator says here. So our calculator said, computer glitch there, 5 over a million was 5 e to the negative 6. That is 0.000005. It's really, really close to 0. So it's approaching 0. So the big idea here is that when polynomials are in rational function form, so we have a polynomial over another polynomial, you sometimes are going to run into situations where you have a large number over a very, very, very small number. And when that happens, your value is going to be infinitely large. And then the opposite will happen if you have a small number divided by a very large number. Then you're going to be approaching 0. So we're going to have both of these situations come into play, and I just wanted to do some numbers with you so you have an idea of what I mean when I talk about them there. They are important for when we talk about asymptote rules. So having talked about large divided by small or small divided by large, today's focus with rational functions is going to be about vertical asymptote rules. So remember that a vertical line is x equals a number, say it's 2, because it crosses the x-axis, x at 2. And our asymptotes are going to be drawn with dashed lines. So we're going to figure out why we have vertical asymptotes. We're going to define vertical asymptotes, and we're going to be able to sketch them in our graph because they act like fences for our graph, and they have that important feature that I was talking about at the very beginning. So let's define vertical asymptote. So a vertical asymptote is a vertical line x equals c, and c just means any value, some number. In this case, it was 2. But a vertical asymptote x equals c is occurs in a function f of x if the function occurs in f of x when the function or the graph increases in magnitude without bound. Graph increases in magnitude without bound. So what does that mean? That means that we're approaching infinity. Okay, so increasing magnitude without bound means it's going to infinity as x approaches c, that x value, whatever that x value is. We're going to do some in a second, but do keep in mind the graph of a rational function cannot intersect a vertical asymptote. So the graph cannot cross vertical asymptotes. And this is important because when we start to talk about horizontal asymptotes, they can cross. So it's important to know the difference. So vertical asymptote occurs when the graph increases in magnitude without bound, and we're going to think of that as going to infinity. So let's look at a very simple example and do XY charts so we can see the numbers and my idea of large over infinitely small things happen. We learned about the parent function y equals 1 over x in our earlier sections, and we could graph it pretty easily from what we know we would do this sort of shape like this and shape like this. But when we did that, we did not define any asymptotes. We just drew the orange graph in there. So today we're going to define the vertical asymptotes for 1 over x. And this is a rational function. This is the straight line 1, and this is the line x, and we're dividing the line into the straight, and this is what we end up with. So we're going to do an XY chart, and we're going to include values really, really close to 0. So this has an implied domain, meaning even if I don't ask you what the domain is, it has a domain restriction. It is that x cannot equal 0. So it can equal any value, but it can't equal 0. But what's interesting is what happens when it gets really, really close to 0. So this is where we're going to get into our vertical asymptotes. So what's interesting is what happens really close to x equals 0. So I'm going to be talking about a big number over a very, very small number. Big over small. So if you look back at your notes, big number over small number, this goes to infinity. And today we're also going to include negative infinity. So we're going to add that to the idea of big and small. So big number over small number goes to infinity or negative infinity. So let's do an XY chart and think about the big over small. So what I'm worried about right now is not what happens on the outside of my graph. I'm just looking at the behavior right around 0. So I'm going to think about what happens at -1 and -2, but then I'm going to stick right here from -1 to 0, and then from 0 to +1 and see what happens. So I'm going to do an XY chart, but I'm going to do it sideways, which is not my norm, but we're going to do that today. So at 0, my function does not exist. You can't plug in 0. And I'm going to do values on either side of 0. So I'm going to plug in, I'm going to sort of like sneak up on it. And I'm going to plug in values like 0.123 1 from the negative and 0.1234 from the positive, and then I'm going to get out to 1. So I'm going to go -0.001, -0.1. I'm going to add -0.5 just because that's all I'll allow in my chart. Maybe I can do more on this side. 0.001, positive 0.1, silly, 0.5, and we'll throw 1 in there. See what we get. So I'm going to use my calculator for this, and I'm going to plug in values in my chart. So I'm going to plug in 1 over 0.5, so the first thing in my chart here, 1 divided by 0.5, and that's 2. So if I divide a number by a smaller number, I get, oh, I didn't do -0.5. That was wrong. Hold on. Clear. 1 divided by -0.5. Better. Oops. Okay, I'm bad at this. 1 divided by -0.5. -2. Okay, better. And then I'm going to plug in 1 divided by -0.1. I get -10. So this grew really fast. The difference in space between -0.5 and -0.1 is very, very small. I'm getting a really tiny number here. So I'm dividing 1 by a very, very small number divided by -0.001. And I've got -1,000. So it grew really fast, but in the negative direction. And 1 divided by -0.1234 zeros and a 1. So that's 100,000. Negative 100,000. So what's happening is that, and we don't normally graph it this way, we normally graph whole numbers, not the very, very small numbers, but at 0.5, I'm down here at -2, which I can graph. At 0.1, it's so close I can't even graph it, but I've jumped down here to -10. At 0.001, so close to 0, it's at 1,000, I can't even graph it. And then at I can't even graph 100,000 for sure, right? It's way, way down here at the bottom of my paper, somewhere here. And so what's happening is that this orange line is approaching numbers that go to infinity. They increase without bound. They increase in magnitude without bound. That's going to negative infinity. So this line, which is a dotted line here at x equals 0, represents the boundary line for my orange. My orange is trying really hard to reach the dotted line. On the other side, this orange line is trying to get to 0, trying to get there with really, really small numbers like 0.001. First it goes through 1, and that answers 1. Divided by 0.5 is 2. Divided by 0.1 is going to be 10. 0.001 is going to be 1,000. So I'm going this way. At 1, I'm at 1. At a half, I jump up to 2. At 0.1, we jump up to 10. At 0.001, I'm really close to 0. I'm jumped all the way up to 1,000. Here I'm at 100,000. And this orange line it's like a fence. It blocks, it doesn't go ever past 0. It can only come up to 0 and then push against it all the way up. So it increases to infinity. And if I added 17 zeros, I would have a humongous number, really, really approaching infinity here. This is the increase in magnitude without bound, vertical asymptote. So what happens is that for f of x equals 1 over x, the domain is x cannot be 0, and where the denominator is equal to 0 becomes x equals 0, the vertical asymptote. So what we're going to do with rational functions is set the denominator equal to 0, and all of those values, with some exceptions, and we'll look at that next, are going to be vertical asymptotes. So the domain and vertical asymptotes are tightly linked together. Let's look at a case where it doesn't, so we can then talk about, do some problems where we do both. Okay, so let's look at this function, which is example 2. So g of x equals x plus 2 over x squared minus 4. So I'm going to look at that on a calculator so you have an idea of what it looks like. So here we have y equals fraction x plus 2 over x squared minus 4. So this looks a lot like the one we just graphed, except it's shifted over, and let's see why. So hopefully you can see it only has one vertical asymptote here. That's where it increases without bound from the right-hand side, and it decreases without bound on the left-hand side. So what we're seeing is this. If we find the domain of this function, the domain is found by x squared minus 4 equals 0. So that's going to be x minus 2 times x plus 2 equals 0. So x cannot be 2 or negative 2. So domain is where it can't be 0. The denominator set equal to 0. Okay, denominator equal to 0. So in this case, I only have the one asymptote. If you look back at the graph, there's only an asymptote at x equals positive 2. So why is that? That comes from the idea here that if we factor it in the rational form, so I factored it, if any of the values from the top and bottom, so if we simplify like we did in chapter 1 right here and here, g of x and this new equation, which I'm going to call h of x, which is simplified to 1 over x minus 2, it graphs exactly the same. And right here is the asymptote at x equals positive 2 from the denominator. This is the vertical asymptote. Note that vertical asymptotes always have to be, there's a P there, always have to be lines, always. So it has to be in the equation of a line. There we go. Now, what happened to these orange factors that got canceled out? What happens is this. Let me show you what the graph looks like that the calculator doesn't show you very well. So here we are at positive 2. So again, I'm going to solve this and say at positive 2, it's opposite math. There's a vertical asymptote here. So this is x equals 2. And I have the same behavior that I did before. We're going to talk about horizontal asymptotes in the next video. But at the value negative 2, no, that's this one. At the value negative 2, I'm going to have a hole. So my graph looks like this. And it looks like this. It's following the vertical asymptote. And then it goes this way. But at negative 2, there's actually a hole here. So we call that a removable discontinuity. Because right here, when I crossed it out, I basically removed it. So holes and vertical asymptotes go together. Hole equals a removable discontinuity. What does that mean? It means that this part of the graph is not continuous here. It jumps over. It's a hole. And that comes from the idea up here that my domain is x cannot be 2 or negative 2. So my graph continues on and it goes forever to infinity this way. To negative infinity, it goes forever to infinity this way. And right here at the vertical asymptote, it tries to get really, really close to the asymptote. But it can never cross because you're not allowed to have positive 2 in the domain. This looks like a lot of work. It's going to be more simple as we do some other problems. So let's see some more. Example 3. Find the vertical asymptotes and find any holes for f of x. So we're looking for vertical asymptotes or removable discontinuity is so long to say, we just call them holes. They occur where f of x, where the denominator equals 0 and doesn't cancel. So this is equal to the denominator, but doesn't cancel. And this is where it cancels. So let's look. X cubed plus 8. That is a sum of cubes. To factor that, I'm going to do that right here in this space. X plus 2. X squared minus 2x plus 4. And then the bottom, I'm going to take out x squared. That will give me x plus 2. So if I simplify this, I can say that at at x equals -2, there is a hole because the factors cancel. And at x equals 0, there is a vertical asymptote. The domain is x cannot be 0 or -2. So let's see what that looks like. We're not really at the place where we can graph these yet, but this will give us some idea as we learn more about them. So x cubed plus 8, and I should have put parentheses, there we go, divided by parentheses x cubed plus 2x squared, parentheses. So I have two different kind of lines than I've had before, but I still have a vertical asymptote at x equals 0. You can see that on both sides it approaches infinity. So that's important. From the left it goes to infinity, from the right it goes to infinity. And if we try to find the value of our function, so second calculate value, at this other value, -2, it's not going to tell me anything. So there's a hole there. It's very difficult to see right here, but if you graph it, you're going to have to include a hole there. So the sketch for this, for you, even if you looked at a calculator, is going to have to include at -2, whatever the graph sort of ends up looking like, it has to have a hole there. You just draw that with an open circle. So this tells you that nothing exists at x equals 0 and there's a hole at -2. So the function continues on, it just sort of jumps over that space because it's not allowed to be a number in this function. It breaks the denominator. So in this section, in this first bit of homework, your goal is to set the denominator equal to 0. Set denominator equal to 0. You also need to factor the top and the bottom. So denominator equal to 0 helps you find the domain where it cannot be 0. Factoring the top and the bottom, if you can simplify, so simplified or canceled factors are going to be holes, and other factors that make the denominator equal to 0 are vertical asymptotes. And you write that as x equals a number. And it's really important that you write as x equals a number. Often students will find the value perfectly fine, but not write it as an equation of a line. So it must be in the form of the equation of a line. So the practice problems you have for tonight are you given rational polynomial expressions where you have to simplify and find the vertical asymptote only. All right? So this rule needs to be something that you write down, vertical asymptotes, on its own note card, because when we add the other asymptotes that are involved in this section, it can be easy to get them confused. So it's really, really important that you have a clear understanding of where vertical asymptotes and also holes. And you need to know the word removable discontinuity, even if for the most part you call it a hole. You need to know where these come from tonight and memorize that. Get it really clear in your head so that we don't get confused when we add other stuff. Okay, thanks.